Alrighty. Cool. Oh, I forgot to link to my. Okay, I'll add that link. I think. Like I said, there's homework posted. Should be on the shorter side, but I feel like there was something else I was gonna say. I just had it. There was something I was thinking about just before class. I was like, oh right, I should say that. And then, all right, I don't know, I can't think of it. If I think of it, I'll tell you. Alrighty, so we're gonna keep talking about set theory. And so, that's right. All right, so we learned about like what sets are and some special names for special sets and a bunch of different ways to write them down. And so then last time we started talking about the idea of a subset, right? And so a subset is defined as, right, A is a subset of B if every element of A is an element of B, right? Formally we say for all A that are in A is in B. And so by that definition, that means that despite the way that we use the word subset in English, every set is in fact a subset of itself. Just kind of, if you just go by the definition, it's kind of obvious. Like, yes, every element of A is in A, so by definition, it's a subset of itself. Okay, and then at the very end of class, I left you with another question to think about. And so I want to start by coming back to that. I'm going to write it up here to remind you, and then I'm going to give you a minute or two to talk to some people around you and see if you all can come to an agreement about what you think the answer to this question is. So the question is the empty set a subset? And we could really ask about any set, but just to make it concrete, I'm going to say the set of natural numbers, just to give us a concrete example to think about. So is the empty set a subset of the natural numbers? Discuss that with some neighbors and decide what you think. Ready, go. All right, thoughts? Yeah, Colin, what do you think?
I could see it either going, I could see it going either way.
You could see it going either way? Okay. It's a very politic answer.
Because it's like, you count the empty set as just a placeholder for nothing. Because if so, then it could, if you count the natural number set having a thing for nothing, then it would be in there, but it does bottom out at 0. So it could also, it's kind of, I guess, how you look at it.
Okay. All right, other thoughts? Spencer?
For all doesn't really make sense to do for an empty set, but like if you think about it as an empty set being less than the set of all natural numbers, then it would be a subset of it.
Okay, so you're saying if you think about it as some kind of less than thing, you think it should be, but the for all doesn't really make sense as an empty set? What you're saying, so maybe it kind of doesn't make sense to ask? Yeah, Jack?
I think you could take into account its negation, and I think that you'll find that it's always true. Because I'd say like if any number in this empty set is not in n, then it wouldn't be 1, and that's always going to be false, and that's a negation, so I think the original is true.
I didn't follow that, but you're
Sorry,
saying,
I'm
no,
saying
it's okay,
like-
but you're saying you want to think about the negation of this?
I'm just saying like, think about in terms of like logic that we use more often. I think that it's almost easier to think about if any. I'm saying it's always true.
Okay, you think it's true,
Sorry.
all right, okay. Other thoughts? Well, so certainly one of the keys, as several of you mentioned, like thinking about this for all, right? If you ever have a question about, whether something is true or not, or whether something makes sense, right? Don't rely on your intuition about what the word means. Just go back to the definition and be like, what does the definition say, right? So, say by definition, I'll say, empty set is a subset of n means for all A in the empty set, A is an element of the natural numbers, right? So it really comes down to a question of, well, what does this mean? We have this for all where the domain is empty. We've actually talked about this before. Does anyone remember? We talked about this? Maybe not. That's okay. When we first talked about for all, we did actually talk about how we should think of it when the domain is empty. But this is maybe the first practical example that we've seen. So what do we do with a for all when the domain is empty? So I'm going to argue that this should be true. And I'm going to show you a few different ways to think about why we consider this true. Okay? So we'll go several arguments why this is true. And so one actually that I hadn't been thinking of, but I think is nice, is kind of what Jack was suggesting. So the negation is, right, if we say not for all A in empty set, A in natural numbers, right, which is equivalent to, we can use a De Morgan law, we push the not over the for all, it turns into an exists. And then we say, not A is an element of n, so we say A is not an element of n. And so this says there exists some A in the empty set, which is not a natural number. I would say this is clearly false. There are no elements in the empty set, so there can't exist one that has any I mean, it doesn't really matter what we say over here. There just can't exist an A in the empty set that has any property at all. Right? So this is clearly false. There are no elements in the empty set. Well, but if this is false, then this was the negation of the thing we were thinking of in the first place, so that would have to be true. Right? Hence, its negation should be true. Right? Another way to think of it is, in terms of this thing we saw, so this is learning goal 6. So this is also a nice little review, or hint or review about this if you've forgotten. But right, when we have for all on some kind of restricted domain, or we can change the domain to be a bigger domain, but then we have to say, include an if. That's like if it's in the smaller domain, then, right? So this is equivalent to, for all, let's say for all A in the natural numbers, if A is an element of the empty set, then A is an element of the natural numbers. Well, the empty set has no elements, right? So this is always false. Something being an element of the empty set is false, right? So this is the same thing as for all A in the natural numbers. False implies A is not an element of, oh wait, did I say not? Sorry, I got tripped up by seeing that above. This should say element of then. Where'd that not come from? Okay, well, false implies anything is true. And, well, is it true that for every natural number, true? Sure. It's just a fancy way of saying true. Now, maybe this isn't that convincing if you don't believe that false implies something is true. And in a sense, like the reason for that is kind of the same as the reason that we consider a for all with an empty domain. It's kind of, we say it's vacuously true. Because yes, it is true that every element of the empty set has this property. Because there aren't any, and so, it's like every $1 million mansion that I own is purple with, I don't know what, I don't own any, so I can make any statement I want, and it's true because it just doesn't say anything, right? And the same thing here, why is false implies something true? Because, well, if this is false in the first place, then it kind of can say anything you want. If pigs can fly, then I own a purple $1 million mansion, right? That's true, I guess, because pigs can't fly, so you can say whatever you want. Okay. So, in fact, yes, the empty set is a subset of N, and more generally, the empty set is a subset of, A for any set A. Even itself, the empty set is a subset of the empty set. And again, this is one of those things that if you just kind of think about what it means, you're like, I can kind of go either way. I don't really know. But things that we've talked about so far are kind of pushing us to say this is true. And we're going to see as we continue we're going to see other reasons that it works out nicely to make this true. Um, what questions do you have at this point? Actually, I just thought of this. Here's a third argument that maybe makes a little more intuitive sense and is not just like focused on logic stuff, right? So, maybe I'll say it out loud first and I'll write it down. If you start with a set, right? The set is a subset of itself, fine. If I remove an element from the set, is what I'm left with still a subset of the original set? Of course, right? I just removed one thing. All the things that are still there are all elements of the original set, right? It just got smaller. If I keep removing elements, right? Still a subset, still a subset, still a subset. Eventually, if I remove all of them, it would be weird if suddenly at that point it flipped and was like, oh, it's not a subset anymore, right? It's just like the extreme where you took out all the things, but it's still a subset because it was kind of what's left over when you took some stuff out, right? I'll say a subset equals what is left over after taking things out. Right? Taking things out, possibly taking 0 things out, but taking some things out, right? That's another argument. Okay. Cool. All right, so now that we have this notion of subset, we can now use that to define what it means for two sets to be equal. And the reason that this is not obvious, right, is because, like, what does it mean for two numbers to be equal? Well, just if they're literally the same number. You can just look at them and be like, they are the same, right? That's what it means for them to be equal. Right, for sets, it's a little trickier because of this idea that we don't care about the order of elements and we don't care about duplicates. And so, if you just write down two sets, they may not look exactly the same, but we might still want to consider them like the same set, right? Like if the elements are in a different order, or if I happen to list an element multiple times, it's like that doesn't really matter, right? So how do we define what we mean when we say that two sets are the same? And there's different ways you could do it, but here's a really nice one. So definition, two sets are equal if each is a subset of the other. So in other words, when I say, A equals B, I'm defining as equivalent to A is a subset of B and B is a subset of A. In other words, every element in A is also in B, and every element in B is also in A. That's what it means for two sets to be the same. They have exactly the same elements. Right? But this nicely gets at this idea that we don't really care about the order or how many times a thing occurs. All we care about is, like, the elements in here are also there and vice versa. They have the same elements. And not only is this kind of a nice way to define what it means for two sets to be the same, it's a nice practical tool. We'll see examples of this through the semester. For now, you can maybe just kind of take my word for it, but it is often an interesting statement. If let's say you have two sets, but they were defined in very different ways, very different looking ways. Right? It may be an interesting mathematical statement to say, you know what, these two things that look like they were defined in very different ways actually are the same. Right? And that tells us something interesting about these two different ways of thinking about things actually are getting at the same underlying concept because they define the same set of things. Right? And so how would you prove that? how would you actually show, oh, these two sets that were defined differently actually are the same? You use this. You say, all right, let's first show that this is a subset of that, and then we'll also show that that is a subset of this. So practically, we can use this to prove that two sets are equal even when they have different looking definitions. Right, and just to give an idea of the like when would you do this, or why would you want to do this? Again, we'll see more examples, but just as a little taste. You know, for example, maybe you have a mathematical definition of some set of things that you care about, and then you also write a computer program that you know, takes things as input and then outputs true or false. And what you would like, your goal was to write a computer program that can tell you, you know, whether things are in this set that you care about or not. But you could say, here's my set defined in this nice mathematical way, and then also I have the set of things for which my program says true. Those are very different looking definitions, but we would like to show, to prove, those are the same, right? That the program actually does tell us about that set, right? That would be a kind of example where you would do this. Or you may just have two different kind of mathematical definitions, which shows those things. So, I want to do an example of this. And it's not going to be a super interesting example, but we'll kind of give the framework of how we're going to do this. So we're going to say let A is going to be equal to the set 2x plus 3, where x is an integer, and B is going to be the set of x such that x is an integer and x is odd. Does that make sense? So again, just to review what this means, right? This is saying we're going to go through every possible integer, x, and for each integer, we're going to put it into this expression 2x plus 3, and whatever comes out, that's going to be an element of our set. So for example, pick your favorite integer. What was that?
5.
5, okay. So 5 is an integer, so if we put 5 in here, we're going to get 2 times 5 plus 3, 13. Okay, so 13 is one of the elements of that set. Right? Also, you know, 0 is an integer. You put 0 in here, you're going to get 3. 3 is an element of that set. Okay? And this one down here says we're going to have the set made of values x, where x is an integer, but also x has to be odd. So we're going to throw out all the even ones. We're only going to keep the ones that are odd. And so this B is clearly just the set of all odd integers. Set A is defined a little differently, right? But prove that A equals B. And it's probably not too hard to convince yourself of that if you think about this, I guess, or if you try some examples. But it's not entirely obvious, especially because, for example, if I changed these z's to n's, this would not be true anymore. This is actually false with n's here. Can anyone see why this is false? Jack?
In the definition of A, there's no way to reach 1, which is an odd instance.
Indeed, yeah. 1 is an element of B, but 1 is not an element of A. There is no natural number x that I can put into 2x plus 3 and get 1. Like 3 is the smallest I can get. Okay, yeah. But if we put Z here, it is in fact true. Okay, so proof. I don't think I'm going to do the entire proof. I'm going to do half of it. And then if you want as an exercise, well, I think I'm going to do half of it. I think the other half is actually written in my lecture notes that are posted online, or you can do it as an exercise to kind of see if you can write the rest of the proof. And then you can go compare to the lecture notes and see how you did, right? Okay, so we'll start by saying, well, you know, by definition, A equals B means that A is a subset of B and B is a subset of A. So we're trying to prove an AND. How do we prove an AND? Just by proving both of them separately, right? So we will prove both. Okay, so or maybe I'll write actually to show A is a subset of B. Well, how do we prove that A is a subset of B? Yeah, Maggie?
Show that all the elements in A are also members of B.
Exactly. So if we go back to the definition of subset, wherever that was, way up here, right? A is a subset of B is defined to mean for all elements of A, like for all A and A is a B. So it's really a for all. And then we can just say, well, how do you prove a for all? In other words, you don't need to memorize an extra rule about how do you prove that something is a subset. You just say, what's the definition of subset? Oh, it's a for all. Okay, so now I know how to prove a for all. Okay. I'll say which means for all A in A in B. Well, okay, my grammar is now messed up. I'll say we must show, which means that, so let A, or no, I'll say let X be an arbitrary element of A, then we will show X is an element of B. Okay? Alright, so now I have this thing X, which I've supposed is an element of A. So what does that mean? Well, we have to look at the definition of A. Oh, I shouldn't have used X, because now I'm going to have X up here. That's going to be confusing. Pick another letter. What letter should I use? Your favorite letter? What?
F.
F? Okay. Well, if F is an element of A, that means, right, any element of A has to look like 2x plus 3. Right? All the elements of A came from 2x plus 3, where x was an integer. So since F is an element of A, F equals 2x plus 3 for some integer x. And then what are we trying to show? We're trying to show it's an element of B, which means we have to show two things. We have to show it's an integer. We already know that. And we have to show that it's odd. Right? We know F is an integer. And also, F equals 2, if I do a tiny bit of algebra, right, it's 2 times x plus 1, which is 2 times an integer plus 1, so that's the definition of being odd. So by definition, F is odd, and hence F is an element of B. That's it. So that's half the proof. One interesting thing to note is that we didn't actually really use the fact that we were dealing with integers. So remember how I said, oh, this would be false if we changed these to n instead of z, right? If you think about this part of the proof that we did, like this part of the proof wouldn't really care about that. It wouldn't change. And so it is in fact true that even if I changed these to n, A would still be a subset of B. And so that half of the proof would be unchanged. The part where you have to really use the fact that you have integers is in the other half of the proof. And so I will let you do the other half of the proof yourself. But if you do it correctly, you should at some point find yourself having to use subtraction, right? And then you have to be like, well, look, this only makes sense if we in fact, since we know we in fact have an integer, then this like -1 or whatever is also going to be an integer, right? And that's where the proof would break if you were dealing with natural numbers and you had to use subtraction. You're like, well, now I don't know that this is going to be a natural number, right? Okay. But like I said, I will. So, you know, other half, right? Showing like that B is a subset of A. I'll leave this as an exercise. Right, and in lecture notes. Okay. What questions do you have about this? Brayden?
How did F, the arbitrary element, come 2x plus 3?
Good question. Because we said it was an arbitrary element of A, and if you look at how A is defined as all the elements of A are of the form 2x plus 3. Right? That's how we get the elements of A, by doing 2x plus 3 for some integer x. And so kind of working backwards, if we know that something is an element of A, then it has to look like 2x plus 3 for some x. Does that make sense?
Yeah.
Okay. Other questions? All right. I want to show you, I guess we don't have that much time, but so maybe kind of do this kind of quickly, but I just want to show you how we do sets in Disco. And in large part, it's going to be kind of what you would expect, right? Because I've tried to make the syntax as close as possible to what we've done. So we can, of course, we can just write down sets using curly braces and commas, the same exact notation that we've been using. And if I put that in, it's like, cool, it's a set, right? The order doesn't matter. Like if I put 3, 1, 2, it actually prints it out as 1, 2, 3, as it's the same. The order doesn't matter, right? And in particular, if I ask, like, you know, are these two sets equal? Of course it says true, right? I can even put in, like, it really doesn't matter if I put, like, if I put multiple copies of things, it's just like, whatever. Gets rid of the duplicates, okay? You can write, you can have sets of whatever you want, like, you know, I can have a set of booleans. You can write the empty set by just putting empty curly braces, right? I don't remember if you can use that special symbol or not, like the O with the slash through it. Maybe if you paste it in, it would work, but. We also can use, you know, like how I said we can use kind of ... you know, to show like a pattern, like if I said 1, 2, ... well, let's say ... 10, right? Right, that works. And just because it would be annoying to remember the exact syntax, like Disco doesn't care if you use commas before and after the dot dot dot. It also doesn't care how many dots you use. Okay, so like that works perfectly fine. You know, you could do, you can count up or down, it doesn't care. You can also do things like if I said 1, 3, 5, dot, 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 you know, 50, it is like, oh, you're counting by twos. Okay, I'll just continue that pattern, right? It counts, so you can get all the odd numbers that way. Let's see, is there anything else I want to show you about that? This is just for fun. You can actually even do like, so for example here, notice right here I skipped by 3 and then I skipped by 5. And so it's like, what's the pattern? So it actually, if you do this, it's like fits a quadratic function to it and continues it. So like this is in fact all the squares. But it's not that smart. It's not like if you tried to be like, oh, let me do all the prime numbers or something like that. Like it's not going to figure out what you're doing. It's not going to get it right. Don't worry about that though. I'm not. That's a fun little feature, but it's not. We're not really going to use it. We can also do set comprehension. So I can say like x, you know, such that x, and I have to use the syntax. I have to use the word in. X is in, you know, 1 through 10, and you know, x is, you know, well, if I just do that, it's just the set 1 through 10. Or I could say, you know, x is less than 5, and of course it will, right? It only keeps the things for which that was true. I can even do things like, you know, 2x plus 7 for that. And so, right, just the same as we learned, it's going to go through 1 through 10, only keep the ones that are less than 5, so 1, 2, 3, 4, and then each of those is going to get put into this formula to give us an element of that set, right? You know, you can do things with multiple variables, like I could say, you know, x times y, you know, where x is in, you know, 1 through 4, and y is in, you know, 1, 10, 100, or something like that. So again, it's just going to give me all possible pairs of values of x and y, and then give the product of each. Anything else? And then really quick, if you ask what the type is of a set, so it says it is a set of, and then it tells you what the type of the elements is. So Disco is, I mentioned this the other day, Disco is requiring all the elements of a set all have to have the same type. You can't have a set, if I tried to say like, oh, a set containing 1 and false, that's a type error, right? But they don't have to, like, you're like, 1 is a natural number, -2 is an integer, so is that okay? Yes, because 1 is also an integer. And so it can just say, yeah, that's a set, oh, I asked the type. It's like, yeah, that's a set of integers. They're both integers, right? If I'm like, okay, I included a positive number, a negative number, and a fraction, it's like, cool, that's a set of rational numbers, no problem, right? And just for fun, you know, you're like, what is the type of the empty set? It says set A. So the A is a variable that says you can put any type you want in there. So this is an example of what's called polymorphism. We'll probably learn more about that later. But all right, we need to do our quiz.